Okay. Oh, wrong screen. Okay, can you see that?
Yep.
So this is our meeting agenda. So I'll just give a few minutes of context. So first, this meeting is recorded. We plan to post it on YouTube. So if over the course of the meeting you have any concern with that, please reach out and then we can adjust. So today we have a couple of guests. Sophie and Maxwell from Matteo Carandini and Canaris Labs have developed a new visual stimulus that were very interesting. And so we wanted to have a discussion. And then they'll present that. And then the rationale for us to do so is that we are in the process of designing the final set of experiment block in our predictive processing experiments. And so our plan is to have this set of experiment here that have different oddball blocks as well as control blocks. And our entire design also could benefit from having receptive field blocks at the end. And so we were planning to have a 10-minute long receptive field block at the very end of the session that would allow to know where the cells are responding on the screen. And Sophie and Maxwell developed a new script. It's just a few months old bioRxiv paper that support in-classroom imaging, that they can map receptor field in just a few minutes, as well as other properties. And so we thought it could be beneficial to introduce this block into our stimulus, and also be a nice collaboration with those folks. And so I just wanted to have that conversation. And Sarah helped us organize this journal club. And so I think that's the context for this meeting. We are in the process. I think the mice that we plan to use for the pilot are the extrasurgery already started. So for you to know, we will probably start to display stimulus in a month to those mice. So if we decide to use it, we'll need to work closely. Okay.
Okay.
Thank you. So maybe you want to share your screen and or how do you want to do your presentation?
Yeah, I can share the screen. Can you see it?
Yes.
Can you still see it?
That's great.
Okay, perfect. Yeah, so I guess I can start directly.
Yeah, as you want.
Yeah. Okay. But so first, thank you, Jerome and Sarah, for inviting us. It's really exciting. I hope you will find the talk interesting. But also, I kept it pretty short, so don't hesitate to interrupt if you want to ask any question. For example, regarding to like the type of experiment you wanted to do, because I was looking through your like the small summary that you show us, but it looks like it's mostly sensory motor experiments. So I don't know how this is going to relate with what we're doing. But anyway, okay. So I'm going to present the paper that on, and what we do in there is to try to map the visual cortex using the zebra noise and a simple model of wavelets for the neurons. Okay, so I'm going to give you a brief introduction, even though you probably don't need it. But so as you might know, when you study the visual cortex, it's very often necessary, or at least very important, to try to characterize what are the visual preferences of the neurons and what they are selective for. And there's been other exhaustive literature that shows that most of the neurons are actually selective for a few features. Among which azimuth and elevation, so like position in an environment, basically, but also orientation of the stimulus, and also like spatial frequency, temporal frequency, movement, and all the stuff. And if you want to characterize each of these properties independently, one would need to run in the individual stimulus, and each of them being specifically tailored to address one of the specific features. So for example, sparse noise for azimuth and elevation, or drifting grating for orientation, or checkerboard moving, and so on. In addition to this, most neurons are noisy. So you might want to run several repeats of the same stimulus for a certain amount of time in order to have reliable response. And what we saw is that usually it ends up in very long experiments that are a bit inefficient. And that's why the idea would be to come up with one unique stimulus that can represents all of these different features and just use it for to characterize all the neurons. So we came up with this, which we called zebra noise. So here it gives you an idea of what it looks like and what the mouse looks at on the screen. So it has sharp edges, high contrast, and it has these stripy motifs with continuous motion. So maybe I can give you a bit more information about what the zebra noise is and how it's made. So basically, it's from Perlim noise, which is a pretty standard type of gradient-based noise, which is mostly used to generate random but natural-looking patterns. So typically, it's used in video games to generate landscape. And here it has another characteristic, which is it's fractal. So you can rescale it and add it to itself according to a parameter that's called a fractal exponent. Maybe Max, you will explain it a bit more into details later on if people want. That basically allows you to parameterize your stimulus. Okay, so we get this type of noise. So it looks like this. We bin the value range. So here it's ranged between 0 and 255. So we bin it in like a certain amount of bins, and then the pixel, according to the bins in which they belongs, are given a dark or light value, and that's how you end up with these stripy patterns. Okay. And you can play with this amount of bins if you want to change or adapt your stimulus to like a specific special frequency, for example. So the advantage of this stimulus is like, despite the fact that it looks very complicated on screen, it's actually very simple to parameterize. So you have a few ways to do it. So you have the comb width. So it's basically the number of bins that you have. Okay, so if you increase it, then you get like very high special frequency. If you decrease it, you've got something more like with patterns, like blobs appearing. You have the fractal exponent that I was mentioning earlier. So it increases or decreases the granularity of your patterns, and you can also control the scale by like zooming in. Okay, so basically you have a stimulus that is very easy to tune, so it can have multiple application. You can use it for different animal species because, for example, we use the mouse, so it has not a very high visual resolution, let's say. But if you want to work with monkeys or like species that are a bit more sophisticated, then you might want to, for example, increase the special frequency of your stimulus. Okay. Another thing that is interesting in the stimulus is that it's it's random noise basically, so it's uncorrelated over space, so you don't have special correlation, and it has uniform. It's uniform across orientation, so it means for every piece of screen, it's gonna represent evenly any orientation, which is nice because then you don't introduce the spatial position to orientation bias. And another thing that is interesting is that it has power over multiple special frequency. So it's not like you have like only one special frequency and that's it. And if it doesn't fit your your neurons, for example, then your experiment is screwed. So yeah, that's basically the advantage of this noise. And something that might be interested to look at is also how it compares with other stimulus, because like one important feature I think for most of the stimulus is to actually capture or like it's to be able to trigger reliably and strongly the neurons. So here the idea is just to compare with like a few classical stimulus like sparse noise. So just to give you like an idea of like how we use it. This is our setup. So the mouse is head fixed but free to run on the wheel, and it has two screens, one in front and one on the side. Okay. we only look with the mesoscope at the right hemisphere in the visual cortex. Okay. And so here, we picked one neurons, and what you see here is the spikes of these neurons during the 3 repeats of the signal. Okay, for like a short bout of it. And we pick the same neurons, and we look at its activity when it's when the mouse is looking at sparse noise. And the idea is to compare. So what you can see just from these 2 figures is that basically, even if the firing is a bit sparser with zebra noise, it actually triggers the neuron very strongly, whereas in sparse noise, it's a bit more noisy, even though you have like a denser firing rate. And to assess if this stimulus actually reliably drive the neurons, what we did is just to look at how repeatable are the neurons across repeats for this. Okay. So here, what you see is basically the field of view of the microscope. Each of the dots is a neurons, and the color, so the darkness, represents how repeatable the neurons behave across repeats. So it's basically the average of the Pearson correlation of the neural activity across the different repeats. Okay, so the higher, the more repeatable. And what you can see is that basically they're just more repeatable when you play zebra noise than when you play sparse noise. Okay, so you can do the same with drifting gratings, and you sort of end up with the same situation where just the activity of the neurons is much more repeatable across repeats with zebra noise than with any other stimuli.
Sophie?
Yeah.
I have a question. In our hands, the locally sparse noise stimuli and calcium imaging is not very efficient at driving activity, as you've shown.
Yeah.
Whereas, so we're moving towards using small gabors to map receptor fields.
Mm-hmm.
Is that what you're showing here, or?
I'm not showing any gabors here. It's just a zebra noise or drifting gratings or sparse noise.
Have you compared the strength of response of zebra noise to small gabors that might be more efficient?
No, we haven't.
Okay.
Because if you have like a single gabors, then you would need to probably show a gabor for each position you're interested in different orientation. So we haven't done that. I guess that could be a good comparison, but no, because the idea was we don't want to like tailored one experiment like specifically. We just want to have like one big stimulus that is randomly generated without having to wonder, okay, so have we presented the same amount of orientation at a point in space and so on. So no, we didn't. But I guess that would be a good comparison.
Similarly, have you guys looked at natural stimuli? Because I think this is a property of natural stimuli, right? That you get these more repeatable responses.
Yeah. So I made one experiment where the mouse first sees the zebra noise patterns and then like a natural movie. What I saw, because it's not in the paper, is that in general it's more repeatable still with the zebra noise. And what I think is happening is that in general, like those very sharp edges that you see in artificial stimulus like zebra noise are actually very good at driving the neurons. Whereas where you show a natural movie, in general, it's it's like the details. It's going to be a bit smaller. The mouse is not going to see the like everything, and generally speaking, it's not going to drive the neuron in such a strong way.
If I might jump in real quick, sorry, Casper. This is all full contrast stimulus, right? Like you don't have any low contrast regions.
No, it's really sharp edges. It's like black and white, and there is no smoothness or anything. Yes.
Sorry, just for Sophie's response from before. This also isn't in the paper, but just anecdotally, I've also done this with natural images and just looked at like fingerprinting ability, and it's a lot higher with the zebra noise. But yeah, that's not in the paper either.
Just for clarity, really quickly, is repeatability really just a function of how strongly you drive neurons, or do you think there's something else there?
Oh, it's totally different. So you can have, I mean, if you strongly drive the neurons, it's going to be easier for, I mean, theoretically, it's going to be easier for a neuron to be repeatable, no? Because if you have like a very low activation, then it's going to be much, like much noisier. So I guess it's linked, but here we don't really. It's not just. I mean, here the plot that I'm showing you is not really about how strongly it drives the. Like if it generates like a sharp spiking activity, but more if this activity is repeatable across trials, which we think is probably a bit more important here.
And okay, yeah, I mean, but in your data, it might just be a consequence of driving neurons more, but it's fine. Sorry, thanks. I think you answered my question.
Yes, Karim?
Yeah. So my question is really about the time representation. So evidently you have some time representation in the way these zebra noise moves around the visual field. Is there a parameter that controls that? You mentioned spatial frequency and scale and fractals, right? So yeah.
Yeah, so you generate this noise in 3D, and basically what happens is like you go through the stack. So you can, like, I mean, what you can do is just to like you generate a shorter bout of zebra noise, and then if you go through it slower, I mean, you're gonna slow down what it looks like on screen. So you can control it, yes.
And have you tested if the strength of these responses is a function of how slow or how fast you dial that parameter?
So we are characterizing the neurons also based on like what we call the drift, which is basically like temporal frequency. But we haven't tested different speed of stimulus really, because what we were mostly interested in is to have like a fast way to characterize the neurons. So basically the idea was to have in the shorter amount of time the maximum amount of information. So we didn't try to like super slow stimuli or something like this, because the idea was like, oh, we need in 5 minutes to span basically the entire space of like orientation and space and spatial frequency and so on. So we have this.
I get that. I get that.
Yeah.
You're trying to determine how, however many you can get within a span of time that could be responsive to your stimuli. But in doing so, there's this time component that is indirectly represented in these zebra noises that could be actually part of the way the response structure or the response amplitude is being displayed. So you're trying to address one component, but then there's another component that gets implicitly encoded somehow in these neural responses that may not be may be unaccounted for, or maybe adding more complexity to the problem.
Maybe
I think
Max, you wanted to
already answered that, didn't you? Well, because with these responses too, you also capture a lot of different temporal frequencies, and so those temporal frequencies are also captured in her response, in her analysis method as properties of the neuron.
Yeah, but that's not controlled by the stimulus, or is it controlled by the stimulus? That's really my question.
There are lots of different temporal frequencies in the stimulus.
And you control that. You can control that.
Yes.
Okay. Oops. No.
Yes. I see another question.
Yeah, it's very technical, but I'm a little confused about the spatial frequency. You seem to show a spectrum, but do you account for the fact that you have these, as you said, hard edges between black and white? So that should introduce a lot of high spatial frequencies.
Yeah.
So the spectrum you showed are really the spectra of the noise?
Yeah.
Okay. So because then I'm a little confused about how do you know exactly what spatial frequencies you have, or how do you control for that? Like, because typically the reason we use Gabors or the gratings is that we're trying to get rid of these hard edges. Because basically, if you look at a hard edge in space, it's a flat edge in frequency space. So it reduces all frequencies. To get a click, you need all frequencies. But these are not low pass filters. So these are hard edges.
No,
so
yeah, it's sharp edges. Yeah.
So then it sounds to me like what you really have is it's not like natural images. You have a lot of high spatial frequencies.
Yeah.
So natural images, okay.
It's really different from natural images, totally. Yeah.
If I might just chime in one more time really quickly. You've mentioned that your zebra noise will be broadband as opposed to narrowband. These drifting gratings, which have like one temporal frequency, will be narrowband versus these zebra noise, partially because they have sharp edges and partially because you have this fractal component here will have many spatial and temporal frequencies in them. Anecdotally, from my own experiences in my PhD in the retina, you can see different computations with a broadband or a narrowband stimulus, and so that's in my experience. I saw that when I recorded direction selective ganglion cells in the retina, if I used a narrowband stimulus like a drifting grating, there was tuning for particular spatial and spatiotemporal frequencies, versus when I used like this broadband stimulus, I used like drifting kinetograms and a couple other things. I saw that tuning would, these neurons would respond at higher spatial temporal frequencies than you would expect, depending on their computation of direction selectivity. So just something to keep in mind, I guess, is that the properties of these stimuli can affect the computations that are being performed in these circuits.
Okay. So you think we would have like drastically different tuning if we had like smoother edges? That's what you're saying?
Maybe hard to say. I mean, and visual cortex is also different from the retina, but it depends. I started thinking about it in terms of like a permissive versus instructive computation, almost like if your circuit is tuned for the absence of one band of spatiotemporal frequencies, or is tuned for the presence of a band of spatiotemporal frequencies, those will get you different results depending on the stimulus that you're using.
Okay, that's interesting. So okay, so I don't know if it addresses your point, but we compare the results for typically orientation tuning between drifting gratings, where it's like the edges are softened out, and the zebra noise, and we usually get the same type of tuning, for example. So I guess it would be more for really like special frequency specific tuning that you would have this effect that you're talking about. Or would it be just that the neurons, for example, they would tend to fire like much faster for like sharp edges, for example?
Yeah, so one hypothetical case that I'm just sort of making up right this moment, right, is if you have a circuit which is computing, an edge that is oriented at some like 45 degrees or something, and that it has tuning for like a 2 hertz drifting Gabor or something. If you have a pyramidal cell which builds up that computation from spatiotemporally offset thalamic inputs or something, then a broadband stimulus that contains this 2 hertz thing, but also has a 6 hertz and an 8 hertz or whatever else, you should still see that computation in that pyramidal cell. Versus if you have a pyramidal cell that computes this feature selectivity from an inhibitory motif, say there's now a inhibitory interneuron which is computing that 2 hertz thing, or computing a 6 hertz thing, and if that inhibitory neuron is activated by this broadband stimulus and now is impinging upon your pyramidal cell, that'll just change what's being computed. Sorry, I don't know if that made sense or is too off the cuff.
Yeah, but that's interesting to keep in mind. Okay, thanks. Yeah. Okay, so basically just to summarize a bit about the zebra noise. So as I was saying, so it's tunable, uncorrelated over space, uniform across orientation, multiple spatial frequencies, and it reliably drives the neuron's response, which is for us what we were looking for. But so as we only have one stimulus that it's basically supposed to account for both the retinotopic position and also the orientation and so on. One of the main problems that remain is that how do we disentangle this feature, since everything is like mixed up in the stimulus? And the way we do it is to use Gabor filters. Why? Because there's been an extensive literature that shows that most of the neurons in the visual cortex, they behave like Gabor, with sometimes more sophistication, but roughly like a Gabor. And the advantage of these filters is that they are entirely parameterizable as well. So basically, a Gabor, as you all know, is just a complex number, which is a complex filter, which is basically the product between a Gaussian and like a sine and cosine. And for in 2D, so it has one position in the screen, so like azimuth and elevation, but also one specific orientation. And you can also add to this like a size and a specific frequency. So the idea here is very simple. It's just to build like a library of Gabor filters to filter the stimulus with these Gabor filters, and then to match each neurons to the Gabor that is the most similar in terms of activity. So to explain it briefly, this is like an example frames of stimulus. Okay. Here we have 3 different Gabors with basically just different orientation. And this is just what the filtered stimulus would look like. And what it would look like if you just take the amplitude and not just like the sine or the cosine. So to match the Gabor, what we do is just to use those filters to build a correlation map, which basically represent for each position of the screen, each frequency, each size, each orientation, the correlation between the neuronal activity for one specific neurons and like all the Gabors basically. So here it's what you see. So so for example, like I picked a specific like one specific neurons, and this point here is a Gabor that is located here in the screen, has this like orientation and this size, and I mean that looks like this, okay? And I filtered the stimulus with it, and I basically look at the correlation between the filtration, the result of the filter and the neuronal activity. Okay, so that's how I obtain these maps. So here I have the highest value like here, which tends to suggest that my specific neurons behave quite similarly to a Gabor that would look like this. Okay, so since it's a complex number, it comes with like a sine and a cosine. But instead of using it, what we can do is just express it as amplitude and phase. And the idea is to express the firing rate of this specific neurons once the like size, frequency, position, and so on are determined as a function of this amplitude, phase, and the phase derivative. Okay, so we build a 3D matrix, which is basically like the firing rate of the neuron as a function of the 3 parameters. Okay, and then you can take this matrix and you can project like on each dimension to get what we called our tuning curve. Okay, so at the end of the day, from just the correlation matrices, you can get the azimuth, elevation, orientation, size, and frequency tuning curve. And from the 3D matrix expressing the firing rate as a function of amplitude, phase, and drift, you can get the tuning curve for like amplitude, phase, and drift. So drift is, I guess it's what we would call temporal frequency. It's basically if you have a Gabor, like how fast it's, how fast it moves. Okay. So you can do it for 1 neurons. Yeah, I see a question, Sarah. I don't hear you. Maybe you're mute. Sorry, Sarah. I think you're muted because I can't hear you. Yes.
Okay, sorry. Wrong setting once again. And a question related to Karim's questions. I'm just not fully understanding how you can dissociate the spatial component of the Gabor placement from the change of the zebra noise stimulus basically frame by frame, right? Because it basically simulates a temporal frequency of the visual stimulus. So how can you basically assign this drift component?
So, okay. So I probably wasn't clear. Okay, so you have, like, was I clear up to here?
I understand it independent of the temporal aspect of the stimulus. So this is a snapshot. One image is present, and then you can basically assign the spatial position of the Gabor filter that you apply to find the maximal drive of activity. But how do you take into account that stimulus changes from one frame to the next, and that essentially is not simulating a motion in a systematic way, right? But it changes for each position of the screen in a kind of a randomized way. But you wanna map the consistent tempo component, which you call drift.
Okay, so
Can I jump in for 1 second quick, just to clarify something, which is that when Sophie showed the stimulus at the beginning, because of teams being a bit choppy, it looked like it was individual frames, but it is a continuous, spatially continuous and temporally continuous. So just making sure that that's not a confusion point.
Was it the confusion point? So I
think the confusion to me is how can you dissociate changes in spatial position and temporal frequency if both happen at the same time in a randomized way? How you
because
do that,
I think I see what. Okay, so we have, you know, those frames, huh? And it's continuous. And one of the assumption is that the Gabor is going to be located in a specific position. Okay. So when I do this correlation here, I basically fix a few property for this Gabor, for this model, which are the position, the orientation, the size, and the spatial frequency. Okay. So when I'm here, like, the spatial frequency is fixed, and I'm not going to, like, try to see if, like, when the temporal frequency increase, does it increase the spatial frequency as well? Like, no. I'm just saying, okay, so this spatial frequency is fixed. And then for this specific spatial frequency, I look at what would be the temporal frequency if the neuron is matched.
Okay, got it. Mm-hmm.
Yeah. And so the way I do it is just, it's very like the simplest way you would think of is just, so I pick the specific Gabor, since it's a complex number and I don't want to, like, care about sine or cosine, I just express it as phase and amplitude. And because I want to account for the temporal frequency, I also look at the derivative of the phase. You know, so I have those continuous traces that corresponds to what a sine phase Gabor would look like when filtering the stimulus, and what the cos phase would look like, and then you combine them together, and it gives you basically an idea of what the phase would be if you had, like, a complex number. Yeah.
Yeah, and got it.
Yeah. Okay, so that's how we get those tuning curves. So you can do it for an individual neurons, but here the idea is to do it for all of the neurons simultaneously. And so if you do that for specific data sets, you get these maps. So here you have the map of azimuth. So it's like if you're red or orange, it means you're looking at the left side on the screen. If you're blue on the right side, you have the elevation maps. So it's color code according to, like, the position in the screen. So blue is, like, up and red is down, and also the like the size, the spatial frequency. Also the orientation. From the retinotopic maps, you can get the sign map. So it's nice because then you can assign, like, regions. So if you're interested in, like, how the different visual area compute the signal, for example. Here you also have a map of the predictability. So what I mean by predictability is, like, how well the model, how good of a job the model does at predicting, like, the neurons. Which, as you can see, it's quite so it's cropped here, but it ranged from 0.2 to, like, 1. Okay, and this is just, like, a summary to try to convince you that the model is actually doing a good job for, like, its simplicity. So basically here I'm showing the predictability. So, like, it's basically the Pearson correlation between the output of the model and the you know, the firing rate of the neurons, and the repeatability, which is what I defined earlier, which is basically the average of a Pearson correlation of the neuron activity across repeats. Okay, so the closest it is to 1, the more, like, the better the model performs. It's It's sort of like an approximation for the explainable variance explained somehow.
So this is the correlation. This is the correlation on the average across your repeats, or this is on a single trial basis, or
on the average across repeats. Because what we want to do is to average out like activity related, neuronal firing.
Still very good. Thanks.
Yes. So maybe something you might ask is how well it compares with classic stimuli. Yeah.
Can you go one back, please? One slide. I might have missed. So what is sign map? What is the sign?
So it's so like in the visual cortex, the neurons are organized according to like the position. So it's you have the smooth gradient where basically the right part is looking on the left side part of the screen, and basically what you can do is to look at the direction of those gradients, and basically when they are together, they're going to be red, for example, and when they are orthogonal or go in different directions, then they're going to be blue. You just do the product of the direction of the gradient, basically, and it gives you those signs. So depending on if it's positive or negative, you color the neurons according to this, and it gives you. It's the way most people define visual area, because you see like a shift in the sign of the gradient, which tend to suggest that you have like a. Well, I wouldn't tell you exactly on the developmental point of view, but you have like something that's developed independently. I mean, it's how most of the visual areas are defined right now.
Yeah, that's probably I'm confused. I'm all new to that because I just see the red not to be, and so I assume the big one is V1, and then
yeah. So this guy is V1, and all the surrounding are higher visual areas. So this guy, for example, is RL, this one is LM, this one is, I think, AM, AL, PM, and it's just depending of like where the sign map changes, basically.
Yeah, so, sorry, but because in the old school world, we would have said the red not to be defines the areas, but it seems, and so that speaks for there's just one area here, but then the sign is what tested it, and so I'm still lost on the sign. Is it the motion direction?
Reference in spatial position. Basically,
but how?
So basically, adjacent areas in the cortex that have opposing direction for the preference of basically the topographic map. And it's just lucky coincidence that that's how mouse visual cortex ended up, because there's no reason that nature would have to flip the sign from one area to the next, but it just happens to have done so.
So the sign is it is the gradient of the red not to be.
Yeah.
It is whether you go left or right or up or down.
Exactly.
Yeah. Okay, thank you.
Yeah. So one question is how does it compare to classical stimuli? So here it's a very simple comparison. So basically what I'm doing is just to look at what the retinotopic map looks. If I play 5 minutes of zebra noise, and I do this analysis compared to if I play 5 minutes of sparse noise. So as you can see with 5 minutes of zebra noise, the retinotopic maps are just much smoother. And if I wanted to obtain the same result with sparse noise, I would need to play this stimulus like for 20-ish minutes. Okay. So the take-home message is just like it's so much faster to run zebra noise if you want to get retinotopies. And something else that you might be interested in is to actually compare the result of the orientation tuning with zebra noise with drifting ratings. So basically here you have the preferred orientation measured with zebra noise, and on the x-axis is with drifting ratings. So as you can see, like for most of the neurons, it just lies here in the diagonal, which is pretty much reassuring.
Can I ask you this is important to me here.
Yeah.
In the cases where they disagree, is this because the cell is very noisy and the measurement is very noisy, or is it because of some break of the model assumptions?
So it's kind of, so there is like several cases where it happens. So for example, here you see it at like around 180 degrees and 0 degrees. So it's probably just because, it's like almost horizontal. So it probably can't really decide of, where it is. Here it's filtered by cells that are very reliable for drifting ratings. So it might be that some cells activity is not fully captured by the drifting gratings either. And also we have some cells that fire in a very sparse manner. And it's really hard to actually like attribute, like, for example, well, I don't have an example here in this slide, but it happens sometimes that you just look at the you know, the spiking of the one cells, and it's gonna have like maybe 2 big spikes, super reliable, but it only spikes twice, and it's really hard to like, you know, like infer like what's going on exactly. So yeah, I don't know. It can just be that you know, like for these specific cells, for example, like the Gabor is not such a great model, but still it responds very well to like a specific orientation gratings. Yep. They're just like, there's a few of them, it's really hard to know what's going on. I think here what's the most important is that according to a Gabor-like model, I mean, for all the cells that should be like, that responds more or less like a Gabor, it's quite reliable between zebra noise and drifting gratings, because then it doesn't necessarily mean that the drifting gratings, I mean, it's really hard to know what's going on, no, because it really depends of what is the actual, I mean, what it looks like, the receptive field of the cells. And it could be the Gabor model that's not good. It could be the drifting grating thing that doesn't do a good job at, yeah, driving the cells either. So it's like, we don't really know.
And in this plot, what will be the proportion of cells that are on the diagonal line compared to outliers?
It's in the paper, but I forgot. It's something like 85% or.
Okay, thank you.
Just a quick follow-up on that, Sophie. When you showed the reliability of your responses, V1 was much better than the secondary areas. So maybe looking at this kind of scatter plot would be interesting to address the question that we basically just discussed, right? In terms of, is there a correlation between the reliability of the response / the noisiness versus the tuning preference? So maybe looking at the secondary areas could tell you a little bit about that.
Yeah, that's, yeah, exactly. No, it's true. Like, yeah, I mean, yeah, there are definitely differences between higher visual area and V1, and like cells in V1 are easier to predict. That's true. So that would be interesting to compare. Yep. Okay, so maybe another question that would be interesting for you is how long does it get a full visual population characterization? So it's basically how long do you have to play the stimulus to get like a nice tuning curve? So here we run it for like 1 minute, 3 minutes, 5 and 6 minutes. And the idea is to see like at you know, like what's the duration from which it doesn't help really to add more minutes of stimulus because it doesn't change. So what we saw is basically from 5 minutes on, you're done. Like you don't really improve your measurement. Okay, so 5 minutes in theory, it's good enough. And for the orientation, you could actually play it a bit longer, but yeah, like in general, I would say like from 5 minutes on, you're good for your characterization. Okay. So yeah.
Really, would the answer here change if you were to use neural pixels, in your opinion?
So we had. So Max has actually like more data than I have with NeuroPixel. I just tried to characterize the neurons with the NeuroPixels. What we saw is that 5 minutes is enough, but then it really depends, I think, of like what's the level of details that you want to go into. Like if you want to get like a quick retinotopy or just get an idea of where the cell is looking at, you probably don't need too long. Maybe if you want to see something like very specific at a specific time scale, for example, then maybe you would need a longer experiment, but this I have no idea because I didn't really look into it. Max, maybe you have more insight since you use more NeuroPixel?
Yeah, so roughly speaking, if you take the same cell in NeuroPixels and the same cell in 2photon, and then look at the reliability of zebra noise in both, it's about anywhere from like 1.5 to 2 times more reliable with NeuroPixels. So, and I think because Sophie, you did the analysis for that one NeuroPixel session, right, and got very reliable things running through the software as well. So
Yeah.
Okay, thank you.
Okay, so just to give you a quick summary. So basically, we have like a stimulus that is completely parametric and tunable with a model that is interpretable. So it's very easy to like associate with real thing was like the output of the model. It strongly and reliably drives the neurons. It's quite fast, so you need like between 3 and 5 times 5-minute stimulus, and you're good to go. So like between 15 and 20 and half an hour experiment, basically. You get tuning curve for like 7 visual feature, like position, orientation, size, spatial frequency, amplitude, phase, and drift. It works both with 2-photon and electrophysiology. We've tested it on like 2 different strain of mice, and it worked well in both cases. And it's open source, so the code is available on this GitHub account if you're interested to test it. Yes.
Yeah, I'm curious if you've characterized the entropy of the population activity under this stimulus versus other stimuli. Is it just related to the entropy of the stimuli themselves? You might understand already my motivation for asking this, or if you want, I can explain why I'm asking.
Sure.
Well, driving a lot of, white noise is really good for characterizing receptive fields because it minimizes correlations between different things. And you showed the correlation of some parameters in space, I think, right? So we image the synapses that come onto neurons. And sorry, there's a baby in the room. We image the synapses that come onto neurons, and we're really interested in characterizing the input-output operations of those neurons. And we would like to drive a very diverse set of patterns of inputs to those neurons. So this is for the SLAP2 experiments that are even part of this. So have you looked at the diversity of population activity patterns driven by different stimuli?
But so what do you mean by like the by that, like, would you mean like the dimensionality of the neuronal activity, or do you mean?
Yeah, I mean, there's different ways to define it. That would be one way to define it. Yeah. So you could do like a modal decomposition, or.
Yeah. So I've looked a bit into it. I mean, it's but I mean, it's high dimensional. Like you can completely compare it to what you would get if you present like a series of natural images to a mouse, for example, and you would look at the spectrum. Then to come back to your question where you were saying, oh, sparse noise is actually very efficient at driving the neurons. I guess it comes with the pros and cons. It's like probably just like a big pixel, like a big square popping out in the screen doesn't drive the neurons so reliably, just because of the fact that the receptive field of neurons very rarely resemble this. So it's good because it doesn't have any correlation, but it's also bad because it's not going to drive the neurons like super well. So here you have something that's it's completely uncorrelated. You might have, because basically everything is happening on the screen at the same time. So you can imagine that if you have this specific subpopulation of neuron that is activated here, it's also going to affect somehow what's going on in the other side of the brain. Probably.
I wasn't saying that sparse noise would be better for this. Sorry, I meant more in like abstractly in system identification. White noise is used, right?
Yeah.
But I don't mean in this particular case. That's great. I think that we might want to quantify this particular quantity because it's sort of like a determinant of how well we can characterize the input-output functions of neurons. I just thought maybe you had quantified it. Yeah,
it's something we looked at, but we haven't. It's kind of preliminary, so I wouldn't be able to tell you something like super. Like what I can tell you is basically the spectrum is similar to like what we saw with most of the, like usual stimulus. Like
if it's similar to natural images, that's fantastic.
Yeah.
Thank you.
Basically that's the end of the presentation. So I'm happy to take any more question if you want. Yes.
Yeah, I have a quick. So first of all, this is beautiful, very nice. Thank you, and thanks for presenting. This is awesome. So you you ended with saying we get 7 characteristics, but you also had an 8th one, which is repeatability. So
yes.
within the 5 minutes, would that be possible for this project that we're doing where it's all about prediction? This might be another interesting dimension for neuronal responses. So is it possible to also get that within 5 minutes, or would you have to repeat those 5 minutes to get the repeatability map?
So you need 5 minutes to span the entire space of parameters, I would say. But then if you want to look at the repeatability, you have to repeat those 5 minutes a couple of times. That's why I think you need between like, I mean, because if you want to average out efficiently like all the activity that is linked to like the mouse running or the mouse doing something else, then I think you would need at least like 3 to 5 repeats, so you can just like get rid of this. And 5 minutes to span the parameter space. Yeah.
But you can also do like a 5 minutes to span the parameter space, and then some shorter block for repeatability is also a possibility.
Also, I guess it depends of like what's the size of the population you're looking at. Because if for example, you're doing electrophysiology, then you're only looking at like one specific like part of the screen. So you can probably like tune your stimulus so you go much faster. You don't need like such a long stimulus, Like, so here it's important because we want to look at the entire visual cortex. So we really need to make sure that each region of the screen like went through all the different like possible size, spatial frequency, and so on. But yes.
Yeah. So thinking through what Alex has just mentioned, this group is merely about predictive processing, and one of the design criteria we use is this oddball, right? I wonder how can we think of the oddball as part of the zebra noise stimulus. This is primarily to scan through everything quickly and save time and so on. But if we're really about, here's the standard stimulus, and then every now and then we randomly inject an oddball, how do you feel, or do you think we could adopt this design in our experimental setup?
What's an oddball?
It's a deviant stimulus. It's a stimulus that doesn't follow what has been presented over the past, few minutes. So eventually the animal sees passively, a bunch of, specific orientations for a few minutes, and then eventually we give it something different, and then we study how the neurons respond to this. The idea is that if they predict what's going to come next, the responses are going to tell us, very predictively, what's going to happen. But if you present an oddball, then they could respond to it in a different way.
I see. That's a good. That's a good question. So
what about inverting? If you invert the black and white at some point.
I think Karim, I think you will have to do analysis on what is it that the system could learn about your zebra noise in the duration that you presented. It's almost like almost antagonistic as what you were trying to do, because you were trying to shorten the time you presented, so that it's almost like there's no way it can learn it. It's like it's this, as Casper said, it's like system identification as the baseline. But if you present this more and more and more, the system will just change, because you're presenting this so much that it becomes more efficient at encoding it. So but it's just a different way to use it.
Yeah, we have to think. I have to think about this a little bit more, but it's definitely a very smart way to screen, things and know spatially and temporally what is responding to what. But I'm just still not linking it with the predictive processing idea we've been working on.
Can I ask 2 quick questions? So one, I may have missed this at the beginning, but for your 5-minute stimulus, or as you increase it to 6 or 7 minutes, is the stimulus repeating itself at all, or is it just always different across?
It's always different.
Okay. And then the other question I had, have you tried, like, if you present the mouse with, for example, natural movies or natural images or something, have you tried using the same Gabor filter decomposition on natural like movies, and does that give you similar, identifiability or something?
Yep. So I've tried that. It's just like you would need a longer movie with natural images if you want to get the same results. Because as I said, I think it probably really depends on the movie you're using, but like mine was really like it's literally like a dash cam attached to an animal, and you would just follow it. But the amount of variability that you have in this movie is much lower than what you would get in an artificial movie, where you make sure that everything is like moving and like going through the entire parameter space. So it takes longer. Like I would need at least like 10 minutes of natural movie if I want to get similar results.
Okay, that makes sense. And then is there a quantification of like after how many minutes, like what distribution of spatial frequencies you sample and at what different locations over like what time you need, or is it uniform, or how does that work with their stimulus?
So we had like a spectrum for like the entire movie.
I see. Okay.
But that's it.
Okay, cool. Thanks.
I have a quick question regarding how you define these curves for each characteristic individually. Because if you, for example, you want to check the spatial frequency tuning, how do you choose the other dimensions or characteristics? Do you just choose the optimum, or?
You mean for the movie? Like how we choose what are the spatial frequency we're spanning?
No, if you for each neuron you compute these curves. I think if you go back 3 slides or so, you have it there, or more. Yeah, this one. So you get the correlation, but I guess that's for one particular filter, right? Where you fix all of the other characteristics. If you think of orientation or so, like the spatial frequency and so on. How do you choose that?
It's based on correlation. So wait,
just the maximum, the maximum and all.
Yeah.
Of the other.
Yeah.
Okay.
So just to make sure I understand correctly the question. So just these parameters are just fixed based on like the maximum correlation matrix that I talked about before. But then the frequency that we're using here and the size that we are using here are sort of hard-coded in the Gabor library that we are using. So it means like I build like a big Gabor library, and I do all the filtering, and then I match the neuron one by one. So it means if I change the spatial frequency that I'm using for my library, then I'm also going to change slightly this curve. So these are just it's like following like a log scale basically on the spatial frequency that the literature says the mouse are sensitive to, if that's your question.
But for example, if you have the frequency, you have to hold the other properties fixed, right? You have to compare the correlation with the Gabors of different frequencies, but at the same size, for example, the same size, or the same elevation, for example.
Yeah. So the Gabor library has like it's like 5-dimensional basically. Like you span all of these for like all these azimuths for all the elevation, and for all of this, all the orientation and all the size, and like it's a huge thing. Yeah.
And I was just asking, how do you marginalize that out so you end up with a 1-dimensional plot? How do you fix the other parameters?
So just the maximum and. I see what you mean. Okay, I just got it. Okay, so you fix all the other parameter and you look at the curve you're interested in. That's how we get the.
Right. And okay, I can also read it up. It's maybe a bit detailed, but yeah, thanks. That answers it. Yeah.
So sorry to interrupt. I will have to go. So for a couple of things. If you can continue, I have to leave at sharp 10. We have a forum on GitHub where we have been discussing, and so I posted the link in the chat. I think I'm gonna have I would ask some questions that are like practical questions related to how to use those stimuli to understand if we can use it practically. And so I would post these on the forum, and we can have a discussion on it. The first thing I wanted to bring up. The second is next week we're going to have another meeting, and this I'm planning to present on classroom imaging. So how are we going to plan our first experiment for the classroom imaging experiment on the mesoscope. So this will be a different topic than today. But Sophie and Maxwell, if you want to join, you of course welcome. This is a very open process. So that will be the agenda. So anybody interested in classroom imaging should come. And what else I wanted to say? Yeah, thank you for presenting. It was really wonderful. I think we'll learn a lot. I still have a ton of questions, practical questions. So if we could continue on the forum, I will value it very highly. But I need to go sharply. But please continue.
Okay, thank you so much.
Thank you.
I just have a quick question for Sophie. So you linked to two GitHub repos. Is one for the stimulus code and one for the analysis that you use with the Gabor filters?
Yeah.
Oh, great. So I think for Karim, if he's still here, for our group, I think we have to make a decision. So it seems that right now we spend 10 minutes or more on orientation tuning. And so one benefit here is we can bring it down to 5 if we use your orientation tuning instead. And it has other benefits as well. But I think another really interesting dimension is actually your repeatability, because I could see it may not be that interesting if a neuron has a certain orientation tuning or spatial frequency tuning for predictive coding, but how reliable it responds, that may very, very well impact that. So I'm wondering if we maybe instead of cutting the 10 minutes down to 5, whether we should use 2 runs and do it twice to get some semblance of repeatability. I think we might even spend more than 10 minutes on orientation tuning anyways. But so I just want to bring it up to the group that rather than saving time, what we actually want to maybe do is use the benefit here that we can get that additional parameter.
What type of stimulus are you using so far for orientation tuning, like drifting gratings, or do you have any other drifting?
I think it's static grading. I think we combine it with receptive field mapping. So I think I might be wrong, but I think we just show patches and do reverse correlation, nothing fancy.
Okay.
Can I just follow up on that, Alex? I think that's a really cool idea. Just one thing about the control or these orientation blocks, that we also have them as a control, right, for the oddball stimuli. So we still might want to have the classic like orientation block, but rather substitute the receptive field one to kind of get a better characterization of what the cells respond to. Just as a thought to throw in.
But yeah. So what do you see the benefit? I mean, here we get orientation tuning as well, right? So we would still get it just in a low amount of time.
Yeah, no, for the orientation tuning, definitely I think this is an amazing stimulus. Just the question, if we want to have a control for the oddball responses, where we show, the orientation in the drifting grading, this orientation, and then this orientation, it would be just nice to have exactly the same stimulus without kind of this temporal structure, which we currently have in this control block or this orientation tuning block. So if we replace it entirely with this, then we lose this control aspect.
That's a good point. Yeah, right. Do you know how much time we spent on the receptive field mapping? Was it 10 minutes?
I think 7 or 6, 7 minutes.
6 point something.
Okay, so then we could do 1 run of zebra noise instead. Okay.
Okay.
Thanks so much again. That is really fantastic work. Thank you.
Well, thank you for having us. And yeah, if you have any question, we're gonna try to use this forum thing. Yeah. Well, thank you again.
Cool. Thanks so much.
Thank you. Bye-bye.
Bye.
Bye.